Welcome back. We're heading into our segment on the derivative as a function. A couple reminders. We know that the derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. We know this is true. Just notice how we're going to denote it though, just reminder on notation. So we could say f prime of x. We could also say dy dx. But when you use that f prime of x notation, you're sort of using function notation. So the derivative of a function f of x with respect to the variable x is the function f prime, whose value at x is this. So just be aware that we might be using the dy dx notation or the derivative notation. A reminder on interpreting the derivative as a rate of change at a point or the slope of the tangent line, see below. I guess I could run through this one with you. Notice you have a function y equals the square root of x. Now I'm not going to go through all the mechanics of it, but what we're going to find is that dy dx, or the derivative, ends up being 1/2 x to the negative 1/2. Now I'll let you go through the definition of the derivative to show that. But notice, if you take and evaluate the derivative at the given point at x equals 4, okay, well, what is 1/2 times 4 to the negative 1/2 power? Well, 4 to the negative 1/2 really means 1 over 4 to the half, which is 1/2, and 1/2 times 1/2 is 1/4. So basically, notice the derivative right at 4, the instantaneous rate of change of 4, is 1/4. So what I'm getting at is, I'm going to use some notation here. F prime evaluated at 4 is 1/4. Now also notice that the slope of the tangent line is 1/4. And that's just a reminder, we made that connection last time, that the slope of the tangent line and the derivative evaluated at a point are the same thing. Okay, a couple lovely drawing here that I wanted to mention. A graph of a function versus its derivative. So the top one is the function, the bottom one is its derivative. I want you to notice a few things, and I'll note over here just so we have a large enough scope. So here's the function, here's its derivative. Things that I just want you to be aware of. Notice here at point B, the slope of the tangent line is negative. Notice point B on the sketch of the derivative lives below the x-axis. Hold that thought. Notice here on the original, slope of the tangent line at point D is 0. Notice d prime is right on the x-axis. And notice here at point E, the slope of the tangent line is very steep positive. Notice that E prime lives above the x-axis. Above, below x-axis, and right on x-axis. So now you can kind of start to say, if they gave me this function and say it was multiple choice, would I be able to choose this as the graph of its derivative? So you really want to think that way. If I throw you a function, would you know multiple choice wise that that was the graph of its derivative? Okay, now let's take a look at the next one. Beware of functions that have cusps or corners or vertical tangents and jump discontinuities. Functions are non-differentiable at those points. Okay, so here we have our famous function y equals absolute value of x. Notice the derivative is not defined at x equals 0. That's a way of saying the right-hand derivative and the left-hand derivative are two different values. It's another way of saying there's a corner. So beware of cusps, corners, and jump discontinuities. Here's some other examples. The function y equals absolute value of x is not differentiable at origin. Oh, sorry, I was reading the wrong one. Here, other examples. This one is an example of a corner where the one-sided derivative occurs. I'm going to highlight it here. Oops, pen's being fussy. See? So here's an example of a corner. This is number 2 is an example of a cusp. Notice it goes like that. So is where the slope of PQ approaches infinity from one side and negative infinity from another. Vertical tangent. So here, right at the point P, I'd have a vertical tangent. Derivative's not going to exist there either. And then, of course, a discontinuity. So here a jump discontinuity. You have a function that goes like this, and then like this. Okay? In blue. So that's just a reminder to be on the lookout for those, because the author's going to ask us, is a certain function differentiable or not? So if f has a derivative at x equals c, I wanted to mention this theorem as well. So if the function has a derivative at x equals c, then the function is continuous. But big note to self, not the other way around. If it has a derivative at x equals c, if it is continuous at x equals c, it doesn't imply that there's necessarily a derivative. So it just goes one way. If it has a derivative at a point, then you know it's continuous. It doesn't go the other way around. Alright, so the problems are 5, 19, 27, 29, and 47. I don't know that we'll get through all of them, but let's try a few. Okay, with this first example, I'll rewrite the function here. It's p of theta is equal to root 5 theta. That's a composite function, so the first thing that comes to mind, hopefully, is the chain rule. Now, we haven't learned, the chain rule is coming up soon. The author's asking us to use the definition of the derivative to calculate for the following function. I'm actually going to go ahead and use the chain rule because you're going to know that by the end of the segment. So p prime of theta, by the end of the chapter, p prime of theta is equal to 1/2 5 theta to the negative 1/2, and then chain rule says to multiply times the derivative of that inner function, which is 5. Alright, so we have the derivative, and we would type that in. And then it's eventually going to ask us, and for time's sake I'm just going to skip to the next part, it's going to ask us to evaluate that at 1, so p prime of 1 is just, we're going to store 1 in for theta. I do want to mention that you could clean this up a little bit and call this 5 halves, 5 theta to the negative 1/2. Let's try typing that in. So you can see I typed it in as 5 halves 5 theta to the negative 1/2, and it said fine. And then we want to evaluate that at 1. So I'll hit pause as you just go ahead and plug 1 in for theta. Now I'm noticing that it doesn't say anything about decimals, so when you have 5 halves, 5 times 1 to the negative 1/2, it doesn't say like a decimal approximation, so we'll just keep it exact. So that would be 5 to the negative 1/2 is really, you're going to have 5 to the 1/2 downstairs. So then that's the same as 5 over 2 root 5, like that. And again, you can see I typed it in that form. Typed it in as 5 over 2 root 5, and it accepted it. And you would perform that same maneuver for p prime of 5, etc. Okay, let's try, I don't want this podcast to be too long, let's try one more together. Okay, I wanted to read this one first and kind of show you what I did. It says to find dy dx evaluated at x equals negative 5, so they're using that notation. if y equals 8 minus 9x squared. Now by the end of this chapter you'll have all the rules, like the shortcuts for taking derivatives, mastered, but notice if I hit help me solve it, it says the definition, the derivative of the function f of x with respect to x is, and they're basically reciting the definition of the derivative, so they're going to assume that you're still using that at that point, but for time's sake I'm going to use, like I said, the little shortcut rules for derivatives. So the derivative of 8 is 0, derivative of a constant is 0, the derivative of negative 9x squared is negative 18x, and then, you know, it says to evaluate dy dx at x equals negative 5, so this means y prime evaluated at negative 5, so whatever negative 8, we're basically storing negative 5 right there, so negative 18 times negative 5 is 90. So that was just exposure to the dy dx notation, basically. A lot of times people see that notation and they're not sure what it's asking. Okay. And actually maybe we do have time for one more, just number 27. I thought this was a good one for all the sort of visual thinkers. Here you have the graph of the function, and then like I said, they're going to ask you to select what's the graph of its derivative. Well, notice the function, you know, is increasing, so that, you know, the little mini tangents would be positive here, and then it's decreasing, and so I'm just going to write here increasing. The tangent line here would be flat, right? Zero, the slope of the tangent line would be 0, and here it's decreasing. So increasing translates to dy dx being positive, and decreasing translates to dy dx being negative, and flat, horizontal tangent line, you know, dy dx is equal to 0. So, you know, increasing, you say, where is it? So it's above the x-axis, and this is the graph of the derivative. And these should say, I just noticed the axes, these should all say y prime. So it's above the x-axis, then it hits the x-axis, and then it's below the x-axis. It couldn't be this one. Here it's below, the derivative is below the x-axis the whole time. It couldn't be that one. And here the derivative is above, below, and then above, and then below. It's too complicated. So survey says, all right, that's good for that one. Hope that helps.